So when we have metals bonding with nonmetals, the electrons get transferred. The metal gives electrons to the nonmetal, becoming a cation. The nonmetal accepts the electrons and becomes an anion. And the opposite charges then attract each other. So the ionic bond is an attraction between opposite charges. And what we do in Lewis theory to represent this is we take the electron dots from the metal and we move them over to the nonmetal. So let's look at potassium and chlorine and show what happens when they transfer electrons and form an ionic bond. So here's potassium is K, and I started to make fluorine, and I want chlorine. Potassium has 1 valence electron, and chlorine has 7. So these guys are trying to be happy. They're trying to, can we see this color? Can you see that red okay, or is that not good? Is that okay? So the potassium is thinking, you know, I've got this 1 valence electron. If I got rid of that, then I would look just like argon. I'd have the same electron configuration as argon. That would be a cool thing. I wonder if I could find somebody to take this electron off my hands. And here's chlorine. And chlorine saying, man, I've got 7 valence electrons. I am so close to looking like argon. I can taste it. I just need 1 more electron. And the potassium overhears him and says, hey, wait a minute. We can help each other out here. How about I give you this electron? And then we're both happy. We both have octets. And so what you end up with is potassium with a positive charge. Now, does that mean it has no electrons anymore? No, it's just that we're now into the core electrons, and we're not going to show those, because then it would look like all of a sudden 8 dots appeared, and that would be confusing. And then over here for chloride now has 8 valence electrons, and it has a negative charge. Now that negative charge can kind of get lost in the dots sometimes, so what we usually do is we usually put brackets around the symbol with its dots, and we put the sign of the charge outside, just to kind of call attention to it, and so that's just sort of a convention. We don't do it with the cation because we don't need to. So now we have a positive ion, and a negative ion, and they're going to be attracted to each other and form a compound, and that's going to be KCl. Any questions? So the chloride ion then has an octet. The potassium atom lost its only valence electron. And what it's left with is an octet in the next lowest shell. So we put brackets around the anion. And this is important to note. In mastering chemistry, the charges are shown, but the brackets are not shown. You hear that? You put the charge on those Lewis structures for the anions, but you don't put the brackets. So please do not text me and ask me how to put brackets in. You can't. It just doesn't do it. Okay? You do have to put the charge on there, but you don't put brackets. Let's do an example. Write the Lewis structure of the compound NaBr. Well, let's think about it from the very beginning. Here's sodium, the atom. How many valence electrons? 1. And bromine, the atom, has 7. 1, 2, 3, 4, 5, 6, 7. So what's going to happen here? Well, the sodium is going to give that one to the bromine, right? So we're going to end up with Na plus and Br with 8 dots. And then if we're not using the computer with mastering chemistry, we're going to put brackets around it and a negative charge. So this is the Lewis structure for the compound. showing the ions sitting next to each other. Any questions? Lewis theory predicts correct chemical formulas. So let's look at barium fluoride and see what happens. What? I think the iPad had a long weekend too. There was just so much that went on. Okay, barium and fluorine. How many valence electrons does barium have? 2. 1, 2. And fluorine has 7. So then, let's see what could happen here. Well, barium could give 1 electron to the fluorine, right? And now the fluorine has a -1 charge, and the the barium has a +1 charge. Is everything great and happy? No. Fluoride's happy. Barium's like, well, I'm better, but I'm still not satisfied here. So what does it do? Well, where there's 1 fluorine, there's probably another one. So here's another fluoride atom with 7 valence electrons. And this barium has 1 more electron it wants to get rid of. So it's going to donate it to a different fluorine atom. And now this has a -1 charge, and now the barium has a 2+ charge. And that's how we end up with BaF2. Because for the barium to get rid of its 2 electrons that it needs to find homes for, there needs to be 2 fluorine atoms to accept those. Let's predict the formula for the compound that forms between magnesium and nitrogen. Well, magnesium. How many valence electrons? Wrong thing. Magnesium. 2. And nitrogen, how many? 3. Sorry, 5. 1, 2, 3, 4, 5. So I'm just going to stick with white. I'm sick of switching around. So what could happen here? Well, we could have this one go over here, and we could have this one go over here. Everything hunky-dory? No. This magnesium's a 2+ now. The magnesium's happy, right? He's fine. The nitrogen still needs 1 more electron. So we will bring in another magnesium ion with 2 valence electrons. And it will give this one to the nitrogen. So now this nitrogen is all good, but here's the magnesium left hanging. What do? Well, bring in another nitrogen. I didn't plan this out very well, did I? So here's this electron. We'll give it to that one. And now this magnesium is good. But we've got a nitrogen over here that's still not good. You're like, is this ever going to stop? Yeah, well, we just need another magnesium. So this electron can go over here, and this electron can go down there. Now this, oops, I didn't want to do that. 2+, and this is 3-. And we shuffled around and transferred until we finally came out even, right? So how many of each do we have? Well, we've got 1, 2, 3 magnesiums. So Mg, 3, and 1, 2 nitrogens, Mg3, N2. We end up with the same formula that we would have from using the rules we learned in nomenclature, where we would look at the periodic table and say magnesium is +2 and nitrogen is -3. The charges are different, so we need to crisscross them. But here we see what's going on with the electrons and why they do that. Because in the process of doing that, each of these atoms becomes an ion with an octet of electrons. They become more stable energy-wise, like a boulder rolling to the bottom of a valley. Everything wants to roll to the bottom and get to the lowest energy. Any questions?